OSID-R e-learning module. OSID stands for Open Area Smoke Imaging Detection. This is the new benchmark in open area beam detection. Beam detection is normally used to cover large open spans within the ceiling space of buildings. Traditional beam detectors with a single photoreceiver are typically susceptible to well-known issues. These range from building movement, foreign object intrusion, dust and dirt buildup, birds and insects, and reflections and industrial light sources. The imaging smoke detector range consists of dual-ended images and emitters, and now the new OSID-R single-ended range, used in conjunction with a reflector. The OSID-R is a reflective single-ended IR detector. The R in OSID-R stands for reflective. A single device covers distances from 5 meters to 100 meters, or 16 to 328 feet. A major step forward in the OSID design is its use of a CMOS imager over the traditional beam's photoreceiver. The CMOS imager warrants the many advantages of the imaging beam detector. The device has a simple, intuitive interface. An onboard heater, is available in conventional versions. Can use the remote electronic test station, and has been designed to accept third-party interface boards for addressability and loop communication. The number one issue that beam detectors face is building movement, particularly thermal expansion, contraction and twist within metal-framed factories and warehouses that are a common sight for beam detection. The OSID-R can accept up to 1 degree of movement in all directions at the detector and 10 degrees at the reflector. As an example, at 330 foot, or 100 meters, 1 degree of flex at the emitter or detector results in a shift of 5 3/4 feet, or 1.75 meters, about its center. The detectors normally operate in the ceiling space of the building, and so generally they will be out of the way of most obstructions, not all. The device is calibrated to ignore transitory obscuration, but if the obscuration is sufficient and persists, the device will go into a fault. Using the CMOS imager, the device is very resistant to external light sources, including bright sunlight, a common failing of traditional beams. This same feature means that reflections from modern building materials, glass and polished stainless steel for instance, will have no effect on the device. Features: a reflective IR detector. Cost effective, only the detector needs to be wired in. A CMOS imager for easy alignment, installation and false alarm resistance. Automatic sensitivity settings. Always the best possible sensitivity for any given distance per UR requirements. Remote test and reset facilities. Electronic smoke test and compatibility with RTS151 key. Installation, lock and unlock. Once the detector is mounted and powered, you can start the alignment. To start the alignment, make sure the red lever is in the unlocked position. This allows for simple operation while working at height, with no risk of dropping a tool, causing delays in installation. The alignment procedure is child's play. Once unlocked and powered up, the eye can be roughly aimed at the reflector. The yellow arrows will quickly start to flash to indicate the required direction of movement to achieve full alignment. Once all of the arrows flash green, the lock button can be applied. The detector now goes through a short sensitivity configuration process, indicated by rapid flashing of the arrows. Once this process is complete, all 4 arrows will flash a number of times, then pause for 5 seconds before repeating the sequence of flashes. This number of flashes represents the selected sensitivity. When the green LED blinks, the device has completed setup and is operational. The final stage of the installation is to add the cover. This provides protection of the mechanism and electronics from insect intrusion and can be painted to colour match the building if required. OSID versus legacy beam devices. The OSID typically takes less than 60 seconds to align and auto-configure. A comparable reflective beam, the 6500 or 1224 in this case, can take many times as long and is much less intuitive, also requiring special tools to operate the micro switches and the addition of a lens cover which must be secured by screws before the configuration process can be started. The 6500, or 1224 in this case, used for comparison on this slide, uses a targeting mirror to enable the initial alignment. This is a clever process allowing the installer to get an accurate facsimile of the device's line of sight. However, the system requires the operator's head to be held in exactly the right place to properly see the target. This isn't always easy, particularly if you are up a ladder. To enable the user to see the reflector, a brightly coloured piece of paper is supplied with the 6500 to be stuck on the reflector. This enables the initial course adjustment, which relies on the user's eyesight. Following this, however, the paper must be removed from the device. Best get the ladders out again. The next step involves using the thumb wheels to try and get the LED readout to the highest possible figure, this representing the accuracy of the device. Once the user achieves this, or gets bored trying, they can start the sensitivity configuration, often with a nagging feeling that they could have done better with the alignment. Heated enclosures are not available, and there is no remote test facility. Now, where did I put those ladders? Testing with a test filter. While the remote test will confirm the electronics and the connection between the device and panel, to test the optics and configuration, the test filter can be used. This covers the lens, or reflector, and should be held in place for at least 60 seconds. During this time, the device should go into alarm. After removing the filter, the device can be reset. It will now blink the alignment arrows to indicate the set sensitivity. The test should be carried out both at the reflector and the detector. Testing for faults can be done by covering the lens with a piece of paper. A fault should be generated within 60 seconds. The remote test key switch drops the emitter power, simulating an obscuration fire event. This is maintained for as long as the key is turned. Once reset, the device will run through its notification flash sequence at the detector or at a dedicated remote fault LED to indicate the sensitivity setting. One of the keys to the OSID's performance is its use of a CMOS imager rather than the traditional photoreceiver. A photoreceiver has an effective resolution of 1 by 1 pixel. The CMOS imager has many thousands of pixels and produces an image of the field of view seen by the device, which the software can interrogate and interpret. The interpretation allows the simple alignment process and supports the tolerance to alignment issues, building movement, and false alarms caused by sunlight or intrusion. The photodiode used by the competition will false alarm when building movement exceeds a small tolerance. It will alarm if any foreign object interferes with the beam, and it will alarm in bright sunlight or reflections hit the beam or reflector. False alarm rejection, building movement. Building movement is a major headache for traditional beam detectors. All buildings will be susceptible to movement, and most large buildings will include expansion joints to account for this movement without stressing the fabric of the building. Metal-framed buildings, often used as the construction technique for factories and warehouses, are particularly prone to thermal expansion, contraction and twist. A small 1-degree twist in the roof beam, to which the detector is mounted, will move the centre point of the beam over 1.75 metres, where it hits the reflector 100 metres away. The OSID can handle partial and complete obscuration of the reflector. This beam blockage is read as a fault and will not raise an alarm condition. The example shows the inopportune positioning of a banner interfering with the beam path. Because the imager is looking for a specifically shaped reflector block, when the reflector is completely obscured across all or part of its surface, the device recognizes this as a fault. With the detectors normally operating in the ceiling space of a building, they often end up sharing that space with insects and birds. The device is calibrated to ignore transitory obscuration, but if the obscuration is sufficient and persists, the device will go into a fault rather than an alarm. There are a range of accessories available for the OSID and the rest of the OSID family. The laser alignment tool is available to help with the initial aiming of the device. There is a mounting kit which provides additional directional adjustability. A heater is available for the reflector. Test filters are available, sold in packs of 10. The remote station provides an electronic device for resetting the detector from ground level. For devices used in sports halls, or otherwise liable to mechanical damage, a wire guard is available. Imaging detection, truly the new benchmark in beam detection, featuring superior performance, excellent nuisance rejection, quick and intuitive installation, all with low total cost of ownership.